All right, first off, sorry for the long delay in getting you your exam 2 grade returned. So the average was 63. We had 2 100%, so congratulations to those individuals. The standard deviation was plus or minus 19, which is, fairly consistent for what we see in this class from exam to exam. The 63 is an improvement, certainly. Not exactly, I think, where we want to be just yet. So my pep talk is going to be that the past couple years have been unpleasant for many people. And we'll need to get proficiencies up a little bit more for the rest of your career at the University of Utah to go smoothly. So, what I'm strongly recommending is that everyone in here take advantage of the office hours time. Come talk to me, right? Come talk to Rashmi or Michael. I think Michael gets hit with a lot of homework questions, but Rashmi and myself are very good resources to go over these types of exam questions, strategies, right? Perhaps why do I write the exam questions in such an annoying, obnoxious way, right? I'm trying to teach and trying to test your understanding of the fundamental equations, and I'm trying to do so in a manner that stresses not the same type of rote problems that we've done in the homework. Right? I want to apply the same equations, the same mathematical concepts, but in a new application area. And that's going to be a common theme throughout engineering. So one of the issues that I see early on in people's chemical engineering journeys is trying to apply algorithms or strategies for all problems. And the more proficient way is always going to be feeling confident with why the equation is the way that it is, and feeling confident about your linear algebra, your computer programming, your differential equations, and applying those in the way that you see fit, right? So once you can apply the fundamental equations to derive a more complicated one, then sort of your engineering brain has to switch off, and your mathematical brain switches on, and you say, great, I got an equation, just need to solve it, right? Then you can go back, double check your units, and make sure that your math kind of worked out through. So the averages this year are a little bit lower, and I don't know if the exams are substantially more difficult. This one would have been quite similar, I think, to the practice exam. Would you guys agree or disagree? Was this much harder than the practice exam?
Someone said much harder.
Harder. It also could feel harder because you didn't have the solutions there as well. But I'm going to post the solutions after class. Give me a little bit to get them on Canvas. So by the end of the day, the solutions will be there. Take a look at them. I went through and I did all the regrade requests as well. On some of them, students were awarded points back. On some of them, they were not. But in the regrades, what I want to stress is just make sure that you make it clear, right, by actually resolving the problem. Some of the regrade requests I got were just sort of written statements. I would like to actually see the mathematical work behind that so it can be really clear where those gaps were. Okay, I'm not going to go over the solutions because I think a lot of these problems, the solutions online will be very clear. So there are a couple of scenarios with like phase diagrams and triangle diagrams where you do just kind of have to know how to read them. But for a majority of the problems moving forward, we're going to have individual kind of Lego bricks, or I guess in my really poor analogy before was the Minecraft bricks, right? Everything we're covering in a lecture is like a Minecraft brick. And every problem that you're going to solve on a homework or an exam or in your future as a practicing engineer, you're going to assemble something unique virtually every time. So put the priority on understanding the bricks, separate that, and then also understanding the assembly process, which is the mathematics. Any questions, comments, concerns about exam 2 or anything moving forward? Okay, so hopefully on Friday, I'm aiming to have the project assigned. We'll talk more about it then, but I've been getting a few questions online. Disregard anything on Canvas about its due date. I'll make sure you have plenty of time to complete it. But basically, it's going to be like a super homework, okay? Really well organized super homework where the calculations will lead up to having multiple processes all linked together, right? So imagine that homework problem number 1 has to feed into homework problem number 2, has to feed into homework problem number 3, and so on and so forth. And then all of these are in one set of code and one big spreadsheet. So if we say, hey, let's change the reactor temperature and lower the conversion, how does that change my recycle ratio to produce the amount of product that I need, right? And that's going to be the ultimate goal of chemical engineering. We had a question, I think on Monday or Friday, when we were doing the acetone benzene flash separation. And someone asked, is this a real process? The answer is no, it's not a real process. The reason why we rely on those simple over trivialized examples to teach you is because the actual chemistry and the challenges of real processes ultimately take an entire chemical engineering degree and oftentimes even a graduate level degree in chemical engineering. So many times if you're designing a new chemical process, you'll be working as an engineer and also with a team of engineers that will have PhDs, bachelors, 20 years experience, all coming together to build these processes. So that's why we have to kind of start with these trivial examples. Okay. So if you got substantially below the average, it's imperative you come talk to me or talk to the TAs. Let's go over strategies, right? The goal is to make sure that everyone succeeds. Yes?
Will we continue to receive homework assignments along with the project as well?
Yes, but they do get lessened a little bit. So the good news is we really only have 2 major concepts left. We're going to talk about one of those today, and that is energy balances on reacting systems. Okay, we've done temperature changes, we've done pressure changes, we've done phase changes, and now we're doing chemical bond changes. Last class we talked about dissolution, right? When you change the intermolecular configuration or change the composition of the system, right? So the last thing that we're going to talk about, the last major topic, is energy balances on reacting systems. At the end, we'll talk about ordinary differential equations and turning this into transient systems, but we only have one major concept left. So that means that the homework problems from now into the end of the semester are basically just going to ratchet up the difficulty and the comprehensiveness of these reacting balance problems. But the good news is that the strategies are fairly algorithmic. The bad news is that they're fairly mathematically involved. But with a computer tool, you can solve these problems very, very quickly. So the homework problems will get a little bit lessened because we're not asking you so many different concepts, but the complexity of the calculations will grow a little bit and require the use of a spreadsheet or Python in many circumstances. So let's get going on that. So what we talked about on Monday is we had this system A plus 2B goes to C plus D, right? And we're just going to say, hey, this is a delta H of reaction is minus 100 kilojoules per mole. So what this minus 100 kilojoules per mole represents, it's a mole of a batch of the reactants to a batch of the products. Right? So this would be 100 kilojoules per mole for every A consumed in this reaction, for every 2 B's consumed in this reaction, for every 1 C created, and for every 1 D created. Okay? So another way that we can write this then is that if I were to insert right, a chemical reaction into our generalized energy balance equation. The delta H that we would be looking for, which would be in units of, let's say, kilojoules, or it could be kilojoules per second if this is a flowing system, would be equal to the extent of the reaction, which is usually units of moles or moles per second, multiplied by the delta H of the reaction, which is kilojoules per mole. Right? So the mole in kilojoules per mole of the reaction is the extent of reaction moles. So it's a batch. It's a chunk of this to a chunk of that. So what if I were to write this 2A plus 4B goes to 2C plus 2D? What do we expect the heat of reaction to be? Minus 200 kilojoules per mole. Right? I'm just doubling everything. Does this equation change in that circumstance? No, because the extent will be different, because the reaction is different, the heat of reaction is different, but the math will all work out just fine. Okay? So this is what we mean by the delta H and the moles there. So one quick point of clarification, or just not clarification, a quick definition. Right, talking about delta U versus delta H of reaction. Within enthalpy, right, enthalpy is defined as the internal energy plus the PV contribution. In a liquid, the specific volume is very, very small. So this PV term is basically inconsequential, right? So in a liquid, the enthalpy is approximately equal to the internal energy. For a gas, that's not the case. So we can rearrange this. U is equal to H minus PV. From an ideal gas, right, we know that PV equals nRT, or PV equals RT. So we can substitute the PV for RT here. And so what we can write then is that the delta U of a reaction is equal to the delta H of a reaction, this is all per mole, minus RT summation of the stoichiometric coefficients. So in this reaction here, what is the summation of my stoichiometric coefficients? Right, what's the stoichiometric coefficient for A? Is it 1? It's -1. -2, 1, and 1. Okay? So I am consuming 3 moles to create 2 moles. So that means every time this reaction occurs, I am consuming some moles of the process. So this reaction here would have a summation of the stoichiometric coefficients less than 0. And if this occurs, then the delta U of reaction would be greater than the delta H of the reaction. If the summation of the stoichiometric coefficients is greater than 0, that would mean that the delta U of the reaction is less than the delta H of the reaction. Now, let's just do a ballpark estimate. R. What do I think are the easiest units for R if we're talking about thermodynamics for energy?
Kilojoules per mole Kelvin.
Kilojoules per mole Kelvin, or moles per mole joules per mole Kelvin. What unit is that? Do you guys remember that number off the top of your head? 8.314. So RT is approximately 8.314. Let's say we're doing this reaction at 300 Kelvin, right? So that means, let's do the math here. 1, 2. So that's about approximately 2.4 kilojoules per mole. Compared to most reactions, it's a fairly small contribution, but something that I just wanted to mention. Okay, so we've already introduced the next concept called, yes, Ethan?
When would we use the delta U reaction opposed to the delta H reaction?
Oh, good point. Forgot to mention. Delta H for constant pressure systems, delta U for constant volume. Thank you for bringing that up. I forgot. Okay, so the next concept is something we've already introduced in this lecture, and that's called Hess's law. Okay, so we talked about what if I doubled this reaction, 2A, 4B, 2C, 1D? What if I increased it by 1.5? So 1.5A plus 3B goes to 1.5C and 1.5D. Whatever scaling factor we use here, we update the heat of reaction. So in Hess's law, we can combine or scale reactions. So an example of this is A plus B going to C with a delta H reaction 1, C plus B going to D, and I'm going to just add these two reactions together. Oh, sorry, it goes to E, my bad. Sorry, didn't look at my notes closely enough. The C's cancel out, so I have A plus 2B goes to E. What is delta H of reaction 3? What do we think it would be?
The two delta H reactions added together.
Exactly. So this would be equal to delta H reaction 1 plus delta H reaction 2. Right? It's just a linear combination of the reactions. I could flip the reaction. So if I had C going to B plus A, what do you think this would turn into?
Negative.
Negative, right? I'm just changing the direction. So I can combine times, right? Scale, divide. I can do all the manipulations, and I just reciprocate those manipulations. So this is the concept of Hess's law. Now this is very important. And let me just put out the example so you have them in your notes. So if we have A plus B going to C, and let's say this has a delta H of reaction equal to minus 100 kilojoules per mole. If I wrote C goes to A plus B, this would have a delta H reaction of 100 kilojoules per mole. And if I had 2A plus 2B goes to 2C, this would have a delta H of reaction equal to minus 200 kilojoules per mole. This is a tool that we use as chemical engineers to basically create all of the data tables that we have access to. And I'll give you a very clear example of that. I want to know the delta H of reaction for carbon plus 1/2 oxygen going to carbon monoxide. Why may this be a really difficult reaction to know? Does anyone want to speculate? Yeah.
It's difficult to isolate carbon alone.
We can isolate carbon alone. Many of you have it in your hands right now. Actually, I don't see that many mechanical pencils. I see one mechanical pencil, right? There's polymers in that as well. Does anyone know another good source of pure carbon? Diamonds. Law of conservation of mass. Heard of it, right? Anton Lavoisier burned a diamond in pure oxygen, measured the weight of the products, and found out that they were exactly the same, right? So law of conservation of mass was coming from burning of diamonds. We have a source of pure carbon, okay? So we can find carbon, we can get oxygen. So why don't we just put these in a calorimeter, light them on fire, and measure how much energy is released when we make carbon monoxide? Yes? Exactly. We cannot tell the atoms what to do. We can't tell the atoms, okay, make carbon monoxide, but don't make any carbon dioxide, okay? And this is actually a very relevant challenge, not the carbon monoxide production, but partial oxidation of hydrocarbons is a current scientific challenge. Hydraulic fracturing, right? So in places like North Dakota and West Texas, they produce mostly natural gas and a little bit of liquid fuels, or liquid hydrocarbons. The liquid hydrocarbons are very valuable because you can put them in a truck, you can put them in a pipeline, you can just send them down to the refinery, or they'll eventually make it into your car for gasoline. But they're producing massive amounts of natural gas. So what do they do with that natural gas? Does anyone know? They just flare it. They just burn it. Waste the energy, throw it away. Because it's cheaper for them just to throw away the energy than it actually is to capture that methane and transport it for sale. So some regions, like particularly in the area around like Pennsylvania, the Marcellus Shale, right, there's a lot of high density population in those areas. So they've converted a lot of their coal-fired power plants, which is also a high density region for coal, right? And they've transitioned away from coal burners to methane power generation, and that's actually the single largest source for why greenhouse gas emissions are slowing down in the United States. It's not that we're consuming less energy, it's not that people are driving more electric cars, it's not that we're putting more solar and wind farms in, it's just that we're switching to methane from coal. That's the majority of our reductions in the CO2 emissions. So what if we could convert methane into a liquid? Does anyone know of a liquid that is really close to methane in composition? Ethane's still going to be a gas. Methanol. So I just need to add in one little oxygen into methane to make methanol. But do you know what happens? The methane just burns, right? It just burns into CO2, so it's exactly the same problem here. So how could we determine the heat of reaction of carbon monoxide formation? Anyone have any ideas? It involves the concept of Hess's law. Can we think of some other reactions that we could add, subtract to get this one to come out? Yes? Oh, you no question? Okay, a pondering hand. Okay. Anyone? Yes?
We could do the formation of O2.
From which sources?
Oxygen and oxygen.
Could. That's a very, very, very high energy reaction. Because two oxygen atoms not bonded together, they would really like to find each other. So it involves, let's just do the same experiment. But make CO2. Right? I'll call this delta H reaction 1. Now let's say I could produce CO, but I couldn't make it 100% pure because the atoms don't listen to what I want them to, right? Instead, I could make a mixture that has some carbon monoxide in it and then separate and purify that carbon monoxide. How do you think I could purify carbon monoxide from carbon dioxide? Does anyone have any ideas of how we could do that? Do they have identical critical points? Do they have identical properties? Yeah.
Maybe through like magnets, carbon monoxide has a much stronger dipole than CO2.
You could. That'd be probably, I think, an expensive process, but it could work. I mean, that's effectively how they separated uranium-238 from uranium-235. We could do a separator, volatility-based separator, right? These two gases are probably going to have different critical points. They're going to have different boiling points. So you could do some sort of distillation process. It would have to be a very cold distillation process, like a cryodistillation. Right? You could maybe think of a selective membrane. My suspicion is that they probably just pressurize this, and then one of the fluids condenses will be enriched in one of the two. So that's my suspicion of how they actually separate these, is just put them in a piston cylinder, compress it, take the vapor away, and repeat the process a bunch of times until it's pure. But on an industrial scale, something like cryodistillation or something like that could work. So it's just distillation, but with very cold bottoms and tops temperatures. Okay, so then we could get carbon monoxide and then add some oxygen and make CO2 also. So how do we combine these to determine the heat of reaction for this desired one here? How can I combine these? Yes?
You want to flip the second reaction.
Okay, so I want to take reaction 1 minus reaction 2, right? That'd be similar to taking reaction 1 plus the negative of reaction 2. So let's write that out. So reaction 1 would be carbon plus oxygen goes to CO2 minus this one. CO2 goes to 1/2 oxygen and CO. Okay? So CO2 cancels with CO2. This one cancels and gives us 1/2 oxygen plus carbon goes to CO. So then our delta H of reaction would be delta H of reaction 1 plus the negative of delta H reaction 2. So if I plug in the numbers here, this first one is minus 394 kilojoules per mole. This one here is minus 283 kilojoules per mole. So minus 394 minus, so plus 283. This gives us that the delta H of reaction is minus 111 kilojoules per mole. So not only is carbon monoxide a poison, it is also an inefficient use of our fuels. So if we're producing carbon monoxide, we're not producing as much energy for the fuel that we are purchasing. Okay, so this concept of arbitrarily manipulating our reactions is going to be critical for us to understand how to do energy balances on reacting systems. There's another way that we can think about this, right? Instead of having these definite reactions that we're manipulating, flipping around, adding together, we can think of just exploding every molecule into atoms and then just rearranging it in the configuration of the product. Right? Thermodynamics is path independent. It doesn't matter what the reaction mechanism is. The reaction mechanism only matters when you want to determine the kinetics of the process, or in your organic chemistry class if you want to control the chirality of your material, right? But if I'm just assembling it, I can just take a house made of Legos and I can break them apart into the individual Legos and then I can reassemble them into a fire truck, right? That's the way that thermodynamics works. Now, if you're designing a real process, you would have to figure out the catalyst that turns a house into a fire truck. But for thermodynamics, I can just take them all apart into individual Legos and I can reassemble them into whatever I want. Okay? So that concept is called the formation reaction, or the reverse of the formation reaction. Yeah. So the first thing is I use the analogy of houses with Lego bricks. So when we're dealing with real systems that follow real physics, right? Do I want to break them apart into protons and neutrons? Do I want to break those protons and neutrons into quarks, right? Where do I want to stop breaking down my Legos? Where do we think makes sense? Yeah.
The electrons?
That'd be very, so those are very high energy processes if I start plucking away every single electron. Because that means, like, if I'm burning this oxygen and putting oxygen here, right, they have the same number of electrons. So I don't need to pluck apart all those electrons. So what I'm going to choose, and not me, this is the thermodynamic forebearers decided that the reference state, right, the reference state is the Lego building blocks. This is our starting point for how we start to construct molecules. Is going to be not the atoms, not the individual atoms, because O2 is a molecule that we find in the world. O, atoms, is not something that we see in the world. It's very high energy, extremely reactive, right? It would oxidize anything it comes into contact to. So we choose as a reference state pure species in their native state at 1 atmosphere and 25 degrees Celsius. And it'll be a little bit different for every single material, but we want to start off with molecules that are going to be abundant, or materials that are going to be abundant and relatively available. So carbon, if I have pure carbon at 1 atmosphere and 25 degrees C, we talked about this earlier, what is a form of matter that it would be in? Solid like diamond, or solid like graphite. So my reference state for carbon is an atom of carbon from graphite or an atom of carbon from diamond. Okay? That's my smallest Lego building block that I'm going to consider. What about for oxygen? Gas. Oxygen is going to be a gas at 25 degrees C in 1 atmosphere. What about bromine? Liquid. Okay. What about lithium? Iron? Neon? You guys got the concept? Good. So then what I'm going to do is I'm going to construct my molecules from this reference point. So all of these enthalpies equal 0. This is my reference state. The enthalpy of oxygen at 1 atmosphere and 25 degrees C is 0. The enthalpy of solid carbon at 1 atmosphere and 25 degrees C is 0. The enthalpy of bromine as a liquid, 1 atmosphere, 25 degrees C, 0. When we calculate delta H's, just as a reminder, H2 minus H1. So if I start off from my reference, okay, that goes to 0. That means all of my delta H's are equal to the actual enthalpy numbers that I put into a table. So that means when we do reacting systems, unless you want to go and measure all of the heats of reaction that every single chemist and engineer has measured, I strongly recommend you choose this reference state. All of the tables are built upon you choosing this reference state. For a lot of the other problems, you can choose the reference state, but you need the data. So you would need to know how much energy is released when you react carbon and oxygen at 50 degrees C and 10 atmospheres. If you don't have access to that data, well, maybe you should rely on the data that people have generated for you. Okay? So the first step for chemical reaction problems is you need to first build your molecules. Right? So your enthalpy values that you'll put into your tables are not going to start off with the inlet stream being 0. They're going to start off with these compounds being 0. And then you build your molecules, and then you heat them and cool them and pressurize them to whatever state you need. So your reference state has now been taken away and dictated because you have to have this information to know how much energy is released when you build the molecules. Question?
So in the case of like CO plus 1/2 O2 is the CO2, could we consider then CO plus 1/2 O2 as having like an enthalpy of 283? Because then it goes to CO2 and releases that? Or is that the wrong kind of idea?
I think it's the right kind of idea, but maybe I'll suggest a different order. This reaction right here, this carbon dioxide, its enthalpy is minus 394 kilojoules per mole because it's final minus initial. This is 0, this is 0. So this CO2, if you were putting this into your energy balance, would have an enthalpy of minus 394 in your table. Okay? This reaction here, this is the same thing. This is the formation reaction. So your question's getting to the next step of our lecture. Carbon plus oxygen, 0, 0. Carbon monoxide. Carbon monoxide's enthalpy is negative 111. So then if I wanted to go back to figure out this reaction, right, I would have to take, this is 0, this is negative 394, this is negative 111, right? Final minus initial, and that would give me this answer here. Okay? So you've jumped ahead and connected the dots already. So the delta H of reaction is equal to the summation of the stoichiometric coefficients multiplied by the heats of formation. This is the heat of formation for carbon dioxide. This is the heat of formation for carbon monoxide. So the formation reaction would be something like H2 gas plus 1/2 O2 liquid goes to H2O, that's a gas, H2O liquid. This is another formation reaction. Okay? This has a delta H of formation, and I'll tell you about this circle in just a second, of minus 285.8 kilojoules per mole. Okay? This little circle means that you're at your reference state. So that little circle there means at reference state. So if your reaction is occurring at 50 degrees Celsius, well, then you're going to have to manipulate this value to figure out what is the heat of reaction going from 25 to 50 degrees Celsius, and these are the strategies that we're going to talk about. But in short, it's going to be the differences in the heat capacities between these two materials. So the path you can think of is, I have hydrogen and oxygen at 50 degrees C. I'm going to cool them down to 25 degrees C. Then I can use the tabulated data to look up what the heat of formation and the heat of reaction is, then I will react them at 25 degrees C. And then I will take from 25 degrees C back up to 50 C. That whole process is the heat of reaction at 50 degrees C. It's exactly the same thing that we did when we talked about the energy balances on the flash calculation, right? We only had experimental measurements of the heat of vaporization at the normal boiling point, which was 1 atmosphere. The difference now is that we only have access to experimental data of what the heat of reaction of this process is at 25 degrees C. So you have to heat and cool your reactants, react them at a condition where you know the heat of reaction, and then heat and cool your products back to the final state. So the concept is the same throughout all of these energy balance processes. Figure out how to calculate a delta H, find the data that allows you to perform that calculation, and then follow that pathway. Conceptually, does that make sense? We will go through it mathematically, but conceptually, that is all we're going to be doing for about the next week and a half, is just applying that concept. Yes?
I just have a question about the tables. Like, they make a lot of sense back before we had computers and we just had like this one table, and these are the values, and we can't have like 50 million tables. Why not now just have like a giant computer database where we just have each of these enthalpies of reaction at every temperature and pressure, and then we're just done, and then we have it forever? Like, why continue to use the tables, which are limited by the state?
Money. These experiments are very expensive. So if you were to work at Dow Chemical or ExxonMobil, they have their own internal libraries where every time someone creates a new chemical, sends it out to a lab to get it characterized, that characterization is hundreds of thousands of dollars. They take that tabulated data and they add it to their own library and their own database. And they don't want to give it to me, right? So the reason behind all of this is because this is the publicly available information that has been supported and released publicly. So a lot of this is government funded or funded by the generosity of people who have paid to have these characterizations made. The other issue is you could pre-calculate a lot of these things, but I know you all think thermodynamics is very, very challenging, but it's actually really, really trivial to solve in a computer algorithmically. So depending on the assumptions you want to make, do I want to model this as an ideal gas? Do I want to model this as a real fluid, right? You can get slightly different answers for making those manipulations. So there is no perfect authoritative final answer because you could actually go into the literature and you may be able to find conflicting measurements of the heat of formation of water as well. So then it comes down to how much do you trust your data sources? Is it worth your time to hire a laboratory team to remeasure these things? Okay, so I just want to quickly go over a couple more things here before we run out of class. Instead of forming liquid water, right, because water is liquid at 25 degrees C. Water is a really useful reactant in the gas phase as well. So this reaction can also be tabulated as the gas phase, but it has a different heat of formation. And this is going to be minus 241.8 kilojoules per mole. Why are these numbers different? I've synthesized water, I've synthesized liquid water and gaseous water. What do they differ by?
The enthalpy of vaporization.
Exactly. But to be more specific, the enthalpy of vaporization at what state? 25 degrees C. So this is difference here is the heat of vaporization of water at 25 degrees C. If you look up the heat of vaporization of water at 100 degrees C, these two numbers aren't going to make sense. That's because the heat of vaporization of water is different at 25 than it is at 100. Okay, so I'll rehash on this and give some more examples, but basically when we take any reaction, and in this case here they're pretty close to the atomic species, but what we're going to do conceptually when we're doing reaction energy balances is we're going to take all of the reactants, we're going to reverse this formation reaction, okay? Stoichiometric coefficient of hydrogen is what?
1.
-1. So if I'm going to explode, let's say this wasn't hydrogen, I have a different reaction here. Let me just write it out really quickly for an example. SO3 gas plus H2O gas goes to H2SO4. Liquid. Okay. If I'm going to explode SO3, I'm going to break it into an S plus 3 halves O2. That is the opposite of the heat of formation, or the formation reaction, right? The formation reaction is S plus 3 halves O2 goes to SO3. So that's why it's a minus delta H formation SO3. Water is going to be a minus delta H of formation of H2O gas. And this is going to be a plus delta H formation H2SO4, right? I'm doing the opposite of the formation reactions. I'm exploding them into their reference state. Then I'm rearranging all of those atoms, and then I'm forming the final product. So that's where this formula comes from. Minus 1 times its heat of formation, minus 1 times its heat of formation, plus 1 its heat of formation. Does that make sense? So this is the opposite of the formation, the opposite of the formation, and the formation. And that's all baked into this lovely algebra of the stoichiometric coefficient multiplied by the heat of formation. And that is how we get heats of reaction. Okay. See you all on Friday. Plan on a quiz for Friday as well.